Hello everybody, welcome to episode number 2 of the BIVBlog, Benedict's IT video blog. My name is still Benedict Stockerbrand, and as threatened last time, today I want to tell you how to run out of IPv6 addresses anyway. First of all, however, one update to the previous episode. In there I explained that with IPv6 we can effectively grow the internet by a factor of about 2 to the power of 24, which is 16.7 million. Now, I reasoned there by comparing the initial allocation sizes for end users. And you might argue that, yeah, but that's not quite the point really, because with IPv6 these days I get a /55 prefix, not a /48, and if you do so the numbers are going to be different. Surprisingly enough, actually they are not, because if you reason like that, you also have to take into account that today with IPv4 you only get at best a single address, possibly not even that, and if you put those two into ratio, so you divide 2 to the power of 56 by 2 to the power of 32, you actually get the same ratio, which is 2 to the power of 24 to 1. So sort of different calculation and result stays the same. And now about today's main topic, how to run out of IPv6 addresses. There are two fundamentally different categories involved here. The first one is how to make others run out of addresses. That's not a technical issue but a business one. So imagine myself sitting here in a suit and a tie rather than a black t-shirt, and to that there a long-term and a short-term thing. As far as the long-term stuff goes, you probably know that with IPv4 we by now have a growing black market, or grey market if you insist so, of second-hand IPv4 addresses. There are people who have addresses they don't really need and they're willing to sell them for a suitable amount of money. This is a business model, and since IPv6 addresses are finite resources just like IPv4 addresses, there is a chance that in the long run we may have a similar situation with IPv6. It's hopefully going to take a bit of time until we get to that point, preferably until I've retired, but that may eventually become a problem for future generations. Ooh. But even today we already have a short-term problem. The regional IP registries, the RIRs, in the case of Europe, the RIPE NCC, they provide addresses to the ISPs, to the local IP registries, the LIRs. And they do that based on the assumption that an end customer will get a /48. But even then, the majority of consumer class ISPs only provide /56s to their customers, for no serious reason. It's enough for them. We know our customers, blah 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 blah. But really, that's not true, and we'll see a bit later on why not. The entire idea here is apparently to distinguish between consumer access and business customers. And that is already some sort of money-making thing that restricts the number of addresses available to others. This is depressing me. So let's talk about how to run out of IPv6 addresses ourselves from the technical point of view. At the last RIPE meeting in Athens in Greece, so the real Athens, not the one in the US, Peter Lodberg, working for Deutsche Telekom, presented their TerraStream architecture, which is their new backbone all the way to the customer network architecture. It was a very interesting presentation, but there was one thing that made a number of people uneasy. We couldn't immediately put the finger on it, but what the Deutsche Telekom plans to do is to encode some not routing related data within 6 bits of every address. In other words, they are wasting 63 out of 64 addresses because they encode this stuff in there. Or they wasted 6 bits out of the 24 we have available. Now, the problem here is that it's not obviously stupid to do so, but if enough people try to do this sort of clever trick, 24 bits are not a long way to go. I mean, they're just 3 bytes of data. And this is very, very dangerous. Now, as far as Deutsche Telekom is concerned, they are only handing out /56s to their customers, so they do have the address space because RIPE and CC allocated them addresses based on the assumption that they are dishing out /48s to their customers. They even have 2 bits left to waste. One of them they actually reserved for that already. But it's still not a clever move in the long run, because if their customers ever decide /56 isn't enough for me for some potential future reason, there's a problem. Deutsche Telekom won't just redesign the backbone, so it leaves people 2 options. Try to find another ISP who gives them a shorter prefix, which is possibly difficult, or look for some kludgy workarounds again, sort of like what we've done with dynamic address assignments and NAT with IPv4 in the past. And that's going to be a pain if that happens. So the idea here is don't waste addresses by encoding things within the address that don't belong there because they're not related to routing. We can do the same thing ourselves. And how's that? Well, if we got a /56 at home, we can start to encode things in there. And even with the /48 in a company environment, we can follow pretty much the same scheme. And here's what I don't recommend. The idea is to fill the bits within our subnet ID, the bits between the global routing prefix we got from our ISP and the interface ID that's used within a subnet with some sort of semantics, so we run out of bits there. And if you have a /56 from our consumer grade ISP, that's just 8 bits to go anyway. So first we start with a single bit that decides if an address is allowed to connect to the internet or not. Second bit is for addresses that are allowed to be accessed from the internet. Third bit is we distinguish between networks for business use and private use. So even if we're an employee, we might have some sort of home office and we want to keep that separate from our private stuff. And in case you have kids, underage kids preferably, you may consider deciding which addresses are allowed to get unrestricted access to the internet and which addresses get access only through some sort of kiddie-proof filter. Next one could be, for example, we might distinguish between trusted and untrusted devices on our side. Right now the European Union is forcing smart power meters down people's throats. And because you don't really control them, but your energy provider does, you should consider them untrusted. I personally wouldn't want to put one of these into any of my networks where I have my own stuff in. So you use a bit to identify networks with this kind of devices. And then sometimes some people do have guests. And these guests might be some long-haired, black t-shirt wearing geeks who expect not only just some booze, but also some sort of network connectivity. So you might distinguish between networks for your own stuff and some guest networks. 2 more bits to go. And the obvious one to go for, which is something that Deutsche Telekom basically did as well, is to use it to identify traffic priority. First one to go is obviously priority real-time communications. In other words, your zip phone. And next is some real-time stuff that's not quite so priority because it's buffered, like your IPTV or internet radio or whatever. Then there's some best effort bulk data sort of stuff like HTTP, HTTPS or email, whatever, where it doesn't really matter if it takes a second longer or not. And last one is low priority bulk data, well, like your kid's zip phone, maybe, or whatever. And at that point, we've already run out of subnets. If we wanted to put, for example, our fridge in a separate subnet than a freezer in the not so far future where the Internet of Things is actually something that's happening, we don't have the addresses to define different subnets if they are otherwise in the same sort of markup we used in these bits. And at that point we're screwed. And even worse, what about real-time simulations? I mean, action games. Those are a different traffic priority class, because if your zip phone is lagging a bit, that's not as bad as your latest, well, online game of what? Doom. Oh, I've heard they released some stuff recently for some emulator or whatever. So if we just follow down this path, we run out of addresses very, very quickly. That's 8 bits in a home environment. In a business environment, it's actually even easier because they just recycle some of these ideas I've mentioned and then decide, okay, these subnets have access to financial data, these have access to human resources data, these have access to research and development, these have access to the management board, network stuff, and as soon as you have a couple different projects running, you're out of addresses in no time. At a customer training a couple years ago, people actually managed literally to run out of addresses within minutes that way. Basically what happened was, after I'd explained how IPv6 addresses are structured, they come up with the idea, oh, so when we have so much space in the addresses, why don't we encode the services that are provided from within whatever given subnet? So we'd have some sort of bit pattern saying, in here we have web servers, or in here we have mail servers, or DNS servers, or whatever. And they very quickly realized, hang on, we have a problem, because we have subnets where there's both a web server and a mail server in there running on the same machine. So they realized, okay, we need individual bits, one for web server, one for mail server, or more. One bit for HTTP, one for HTTPS, one for SMTP, one for IMAP, one for DNS, one for SSH access, one for backup, for blah, 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 blah. And within about 10 minutes, they were running out of bits. And I pointed out to them, folks, you've just run out of addresses already if you continue that. Well, then we need more addresses. Folks, you've got a /20 something, and that's a whole lot of addresses. So that should be more than enough, unless you start wasting them like that. And at that point, somebody came up with, well, but with IPv4, we have a /16. I don't see a reason why we can't have a /16 for IPv6 as well. I mean, if everybody did that, the IPv6 address space would already be as exhausted as the IPv4 address space is today. At that point, I was simply so shell-shocked. I couldn't find a reasonable answer for that. It was just so surreal. They were clever people and they knew their job about IPv4, but at that point they simply couldn't mentally cope with the fact that IPv6 addresses are large, but they are still finite. So if you set up IPv6 and do an address plan, which is probably come up one of the future episodes where I explain how to do that in a reasonable way, just keep in mind IP addresses are for routing and you're not very well advised to encode anything else within the address. Now at the IETF meetings, the meetings of the Internet Engineering Task Force, where the specifications for the Internet are made, it's apparently a kind of annually recurring event that somebody shows up with, hey, I've got a cool idea, why don't we encode geolocation information in addresses? And they're invariably politely advised that no, this is not a good idea, maybe go home, work the numbers. And I've been to a couple of IETF meetings. I had never seen that happen. I've seen a couple other funny ideas being presented there, but why don't we do the numbers right here, right now, and hopefully take the pain from future IETF meetings. Now, if we assume that we want to encode addresses with a 1 kilometer resolution and take a world circumference of about 40,000 kilometers, we need 16 bits for latitude, 16 bits for longitude. So that's 32 bits we are wasting within an address. And we have 24 extra bits from the move from IPv4 to IPv6 anyway, so we've been running out of addresses already. And if that's not good enough, why not go down to a resolution in meters? Adds another 20 bits. And at that point, we've wasted 52 bits within every IPv6 address, more notably in the subnet prefix, and those are only 64 bits long, so we have 2 to the power of 12 addresses available, or subnet prefixes available within every location. Sounds impressive, but doesn't necessarily work in places like, I don't know, New York City, Rio de Janeiro, Paris, London, I don't know. So this is a stupid idea and it doesn't work, no matter how exciting it sounds. In summary, people, no matter what you do, when you come up with an address plan, don't encode anything in there but routing information. That's the only stuff that belongs there. Otherwise, you'll realize that IPv6 has a tremendously large address space, but still IPv6 addresses are only 16 bytes long, and 16 bytes isn't long enough for a number of people to even hold their email address. Remember that. So much for today. I hope you enjoyed it, and if you want to discuss or want to take a look at the references, move over to the forum. Otherwise, hopefully see you next time. Bye.